All right, here in chapter 3, we are taking a look at correlation, finally. Correlation is a test that has bounced around in the latest two or three editions of the book that we're using, and it found its way to the earlier parts in chapter 3. But I want to save it for later on for a couple of reasons. One, because even though this edition of the book doesn't really talk much about it, we use a t-test in order to determine significance. And in this version of the book really didn't delve into that into chapter 3, but I wanted to add it into this presentation because we know how to do a t-test and we understand what the purpose is of it. And I also like to save it for last because it is not a test that relies on population parameters. So it works really well to put after all the T and F tests. That way we get into a different kind of test. So that's why I chose to do it now. In former editions, it used to be chapter 11, but you don't care about that. That's fine. So let's talk about correlation, and we are talking about what's called bivariate correlation. Bivariate means two variables. And for a bivariate correlation, we must have two scale variables. Okay, we can't use nominal variables, and we shouldn't use ordinal variables. There is a way to do correlation with ordinal variables, but we're going to just stay away from that and rely on two scale variables. So when we talk about scale variables for the purpose of this test, we are looking at something like maybe on a scale of 1 to 10, how happy are you? Or the number of times that something has happened, like the number of times a battle was won on foreign ground. So we can measure things in terms of frequency, duration, intensity, but it has to be on a numeric scale, and it should be on at a scale level of measurement for what we're going to do. So don't think about things like nominal variables like political view. So maybe Republican, Democrat, Independent, Green Party, whatever. Those are not going to be something that we can use for a correlation. And don't think about like satisfaction scales like how satisfied are you with our services today? And you say, well, no, not satisfied, mostly not satisfied, neither satisfied nor dissatisfied, mostly satisfied or very satisfied. Those kinds of things, although we can order them, they tend to be ordinal, and we stay away from them for the purposes of this. Even if you assigned a number to it where 1 was not mostly and let's see, 5 was very satisfied, or excuse me, 1 was not satisfied and 5 was very satisfied, that still doesn't quite work because the distance between a 1 and a 2 isn't necessarily the same. We can kind of wiggle around it if we just say, like, on a scale of 1 to 5, how satisfied were you? And don't worry about what the scales mean. So once you enter these kind of names into the scale, it tends to wash out the objectivity of picking a number. So again, we recognize that there is some wishy-washiness to it, but once you have ordinal positions where the distance between them are not equal, it starts to really hamper the method of doing the correlation. So let's jump into some of the visual aspects of correlation, and that's the scatter plot. The scatter plot is a visual representation that's based on what are called ordered pairs. You might remember that from planar geometry in high school, where you talked about the coordinate plane and the y and x axis and everything. This is the example from the book. I used an Excel scatter plot for this, so it's a little bit stretched in one direction. I suppose I could squeeze it and see what happens there. Yeah, that's close, and a little bit closer, and that's not too bad. So there we have kind of a clear representation to where the distances between the intervals are graphically close to the same. But that looks kind of funny on the page. So I'll leave it back here where it was. So the scatter plot has ordered pairs, and what it has is one person, for example, has a score on the x-axis and a score on the y-axis. This is the example from the book where we're going to be talking about the number of hours slept and mood the next day. So you measure the number of hours slept on one axis and the mood the next day on the other axis, and each person gets 2 scores, the number of hours that they slept and the mood that they had the next day. That's why each person has 2 scores. All the numbers on each axis are called intervals. That's kind of a hint as to why we want to have an equal interval variable for each variable that we're measuring for a correlation. And the x-axis is the horizontal axis, the y-axis is the vertical axis. Again, you probably remember that from planar geometry, and if it's not rushing back to your mind, it will probably by the end of this presentation. So let's look at the data that goes with this example. So we measured mood, maybe like on a scale of 1 to 10, where 1 is not happy and 10 is very happy. So we measured mood for 6 people, and we also measured the number of hours slept. So each person, so the first person has the number of hours that they slept and the mood that they were in the next day. And so for example, the last person slept for 10 hours and has a mood of 6. And you can see where these all fall on the scatter plot. So the last person who had the hours slept of 10 had a mood of 6. So the sleep in hours is all the way over at 10. Okay, and the mood is all the way up at 6. So where those two lines intersect is the point where that person is. Pretty self-explanatory. I'm not going to dwell on it too much. So that's the example we're going to be working with. Before we get into it too much, let's take a look at some examples of the type of correlations that we can have, and we'll do that using the visual representation, looking at the strength and the direction of the relationship. So some of the patterns that we have are linear, meaning that all the dots tend to kind of flow in a line together. Even though they're not exactly on this line, we can put this blue line in here that kind of represents where the general trend goes. So that's called a trend line. The linear relationship tends to be this kind of curved type of trend to where the data seems to start low, peak, and then become low again. By the way, this could be an inverse curve to where it's U-shaped as opposed to this hump that it creates. Or we can have no correlation at all. With a positive linear correlation like this, it could be something like shoe size and height, where the taller you are, the bigger your feet are, maybe. A curvilinear relationship could be something like how much responsibility you have throughout your lifetime. So if we put how old you are on the x-axis, so as you get older, okay, you start out with a little bit of responsibility. So responsibility starts out really low and goes really high on this y-axis. So you start out with very little responsibility as a child. As you become older into adulthood, you have a lot more responsibility. Then maybe as you become an elderly person, you might have less responsibility because maybe you're living with a family and they take care of some of your needs, or you're living in an assisted living home and again, they're taking care of many of your needs, so you have fewer responsibilities. Then we have a situation where there's no correlation, which is indicated sometimes, not usually, but sometimes by just a flat line, meaning that as one variable increases, the other variable has no appreciable change. This could also be a vertical line. Sometimes it's just not there altogether. It just depends on who is developing the scatter plot. But a no correlation scatter plot would be something like shoe size and IQ, where there is probably not a significant correlation or any real relationship between shoe size and IQ. Now, when we talk about linear correlations, we're talking about direction. We're talking about a positive correlation or a negative correlation. Again, a positive correlation could be something like height and shoe size, okay? Or a negative correlation could be something like the number of hours you work and your satisfaction. So you could work more hours and become less satisfied. So if we have a satisfaction scale on the y-axis and a number of hours worked scale on the x-axis, as the x-axis increases, so as your number of hours increase, your satisfaction decreases. You could also say the same thing for homework and satisfaction, but ideally you'd like to do homework because it increases your learning, blah, 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 blah. Okay, we'll move on. So the strength of the correlation is indicated by how clustered the points are around what we call a trend line, or just around a central line that tends to go through the middle of all the data. So in this particular case, and maybe I'll get a quick trend line drawn real quick. Let me insert that shape right quick. So if we had a trend line that kind of looked like this, you can see that the data tends to be spread out around that trend line. Again, I'm just kind of placing it arbitrarily so that you can see. what the data might look like if it's centered around a trend line. It's not a precisely placed one, but it's pretty good. On the second example, you can see that the trend line might be about the same, but the data tends to center around the trend line a little bit more. So that strength becomes a little bit stronger. So the strength of the correlation between those variables becomes a little bit stronger. And then in the last example, it's even stronger yet. If we had a perfect correlation, those lines would all fall, or excuse me, those dots would all fall on the line. There'd be no difference. Okay. And then in the bottom set of examples, we have, let me get this trend line oriented the right way. We still have a weak correlation, but it's a weak negative correlation. So the top and the bottom examples might have the same strength, meaning that they're weak altogether, but they're just weak in different directions. And that works for a little bit stronger correlation and a little bit stronger yet. So in the top and bottom, we're going to consider those to be equally strong or equally weak, depending on what the situation is, but they're in different directions. So we have strength of correlation, we have direction of the correlation. Now, we don't just rely on a visual representation of a scatter plot in order to help us determine the strength and direction of the relationship. We use what's called a correlation coefficient. It's a number. And what's nice about the correlation coefficient is that it's a pretty standardized number. And really what it is, it's a number that goes from -1 all the way to the +1, including 0. A -1 indicates that it is a perfect negative correlation. A +1 means that it's a perfect positive correlation. And a 0 means that there's no correlation at all. So if we had a perfect negative correlation, it would be represented by dots that create a line. Well, if you drew a line through it, but they're dots that create a perfect line in the negative direction. So that as one variable increases, so as you go further to the right on one variable, the other variable decreases. A perfect positive correlation is again a perfect line, or as perfectly as I drew that line, a perfect line in a positive direction. That's as strong as two variables can be correlated. A no correlation is indicated by dots that seem to be random, that you can't really see a trend develop, and that has a correlation of 0. So the further you get away from 0, the stronger the relationship is. And if it's positive, then it's a positive correlation. If it's negative, it's a negative correlation. So for an example, our coefficient, if we had a correlation coefficient equal to -0.68, the sign would tell us the direction. So we'd have a negative correlation. And then the coefficient, the number, would tell us what the strength is. So the sign tells us the direction, the number tells us the strength. And as we get closer to 1, that or -1, that gives us an indication that it's becoming a stronger correlation coefficient. Now, we can't just rely on a visual representation because sometimes it's not just clear cut. Now, here I have a correlation matrix. Sounds like a really fancy thing, and you can tell your friends you learn about correlation matrices today. And really what it's saying is that if I had a set of variables in variable 5, 6, and 7, if I looked at all the possible correlations between those variables, this is what I'd get. And this is called a matrix. So there you go. So if we looked at variable 5 and variable 6, and we looked at the correlation between them, you can see that there's kind of this hodgepodge of dots, and maybe possibly it has a slight negative feel to it, but it's really hard to tell. So looking at this, we can't really tell just based visually, which is why we rely on that coefficient. And by the way, in this example, these two matrices are identical. They're just rotated because they put one variable on the x-axis. So for example, in this correlation scatter plot, we have variable 6 is on the y-axis and variable 5 is on the x-axis, and then it's flipped here where variable 5 is on the y-axis, variable 6 is on the x-axis. So when you see the red lines connecting those are actually the same matrices. They just happen to have the variables flipped on the axes. But if you look at these two, where we look at the correlation between variable 7 and variable 5, you can see that there's a pretty obvious positive trend. Okay, and if you look at the correlation between variable 6 and variable 7, you can see that there's, again, probably not a correlation there. It just tends to maybe a slight negative correlation, but really there's probably nothing there. But again, we can't rely on the visual representation. We must rely on statistics in order to tell us what the strength and direction are, because it's not always abundantly clear. Now, when we talk about a correlation and we want to find out basically how far away these dots are, these ordered pairs are, from a line that kind of represents the mean. This is what we call a regression line, but it's the trend of this data. And we want to find out how strong this correlation is. And we do that by looking at how far each ordered pair is away from this line that represents kind of the mean here. So if I have some scores, and these are kind of just random scores, I can see that the green line that goes between the ordered pair that looks like it's at 8 over and 2 up. If I look at that ordered pair, I can see that it is quite a long ways away from kind of the mean of these data points. Whereas this ordered pair, which appears to be at 4 over and 5 up, that is very close to the trend line, and some of them fall exactly on it. Now, as you can see, the area, if we were to calculate the area that is inside of this triangle, it's pretty large. And if we took all of these points and made these triangles out of it, we could add up the amount of area that each dot is away from the mean, and we could come up with some kind of figure and say this is how far away all of these dots are all together. And if we divided them by the number of dots, we would come up with the average amount of distance that all of these points are from the mean. That's kind of what we're going to be doing, but we'll do it mathematically, not like calculating the actual area underneath that triangle. But as you can see, if all of these dots were much closer to the trend line, then we would have a very strong correlation. But if they were all much farther apart, we'd have a very weak correlation, because we'd have a lot of variance or a lot of distance from the mean or from the trend line. In this particular example, by the way, we have an R coefficient of positive 0.765, so it's a pretty strong correlation. We know it's positive, but we also know that it has a p-value of 0.00864335, which means that the likelihood that that we find this strong of a correlation is much less than 0.05. It's actually 0.008. So that's just interesting, just to put a number to it. So this is a strong positive correlation. It's significant. So let's take a look at the formula for calculating the R coefficient. Now, this is a formula that we can use to calculate the R coefficient that uses raw scores. So if we had the raw scores for the hours slept and the mood, we could plug all that information in here and come up with an R value. And kind of, I'll just walk you through the logic of it, and you can kind of see what's going on here. We find out how far each X value is from the mean of all the X values. And then we find out what the Y value is minus the mean of all the Y values. Then we divide it by the total amount of variance, using the sum of squares in this case. We find out the total amount of deviation that each score is from the Y-axis, multiply it by the amount of deviation that each score is from the Y-axis, and that gives us our R coefficient. Let me bring forward that table so we can kind of look at our data again real quick. Let me bring this table forward. Oops, wrong slide. And here we go. See if it fits. Go away. There we go. Plugged it in as text when I tried to plug it into my text box. Okay, so what we do is we find for all of our X values, we want to find the mean of all the hours slept. We want to subtract the hours slept from each of the actual scores to give us the deviation score. We've seen that before. We do that same thing for all the Y values, and then we multiply the deviation scores for the Y values times the deviation score for the x value. I said that backwards. The x values for the y values. So we multiply those deviation scores, which is what we're doing in the top here. Then we add them all together. That gives us a total amount of deviation. Then we find the sum of squares for the hours slept. We find the sum of squares for the mood. And then we multiply those to give us a total amount of deviation. So we divide all of the scores, deviation scores by the total amount of deviation, and we're good to go. That gives us our R coefficient. Now, there's a lot going on there, and we're actually going to walk through this using a different method. But it's very similar. And what's nice is that the formula looks cleaner, but we're actually going to end up doing the same amount of work. But anyways, we're going to do it using our z-scores. Now, we're going to do the exact same thing, believe it or not, but we're going to do it using z-scores. So instead of using the actual raw scores for the hours slept and the mood, we're going to convert all of those to z-scores because we know that once we find the standard deviation of all of those hours slept and the standard deviation for all of those moods, we can find out how far away each score is from the mean in terms of z-scores. We've seen that before. That's the z equals x minus m divided by SD formula that we've seen. So here's what we do. We multiply the distance that each x score is. So we multiply the distance that each hours slept is from the distance that each mood is from the mean. We multiply those together. We do that for each pair. We add them together and divide them by the number of pairs, and that gives us the mean distance that each ordered pair is away from the mean. It's the exact same thing, and it arrives at this same conclusion, where we're going to find out how far away each score is from the mean and divide it by the number of pairs. We're going to do that using the z formulas. So if we go to our example, we have our raw scores listed here, and I've kind of inserted a trend line that kind of talks about where those points, a line that kind of goes through the middle of those points there. It's a little bit different than a mean line, but it kind of gives you the idea of where those lines tend to center around. So this is what we're going to be working with, and we're going to convert all of these ordered pairs into z-scores. So instead of talking about hours slept and mood, we're going to talk about the standardized distance, or the z-score that each score is from the mean. So let's calculate the R coefficient with our new formula. So in order to calculate the R coefficient, which will tell us the strength and direction of our relationship, we do some stuff that's all the way back to chapter 2 and 3. It's pretty interesting. So we take the sum of all of our z-scores for the x variable, which is hours slept. We take the z-score for all of our y variables, which is mood, and we divide it by the number of pairs. So let's step through this for a second, because in order to get to our z-scores, we have to calculate some other things. So I took all of my x values for hours slept. I found the mean number of hours slept, so the mean of x equals 7. I subtracted the mean from the x scores to get my deviation scores. So if you slept 5 hours, you were 2 hours below the mean. I squared them to get rid of the negative signs, which would lead us to 0 if we added them together. We add our squared deviation scores and we get 16. We divide it by n, which gives us our variance, and then we take the square root, which gives us the standard deviation. So on average, people slept 7 hours with a standard deviation of 1.63. Now what we can do is we can convert all of our hours slept to z-scores. Each score is subtracted from the mean, which gives us our deviation scores. We've seen that already, but x minus m divided by SD. So what we do is we take 5 minus 2 divided by a standard deviation, which we found to be 1.63. The first hours slept of 5 has a z-score of negative 1.23. So if you slept for 5 hours, you were 1.23 standard deviations below the mean. The next value of 7 has a deviation score of 0, which means that it is 0 standard deviations, or has a z-score equal to 0. And that makes sense, because if the mean of our sleep hours is 7 and you slept for 7 hours, you are 0 standard deviations away from the mean. And you can see how the rest were calculated. We do the same thing for our mood. We take the mood that everybody had. We find the mean mood, which was 4. We find our deviation scores. We square them. We add them together, divide them by n to get the variance, and take the square root of that to get the standard deviation. Once we have the standard deviation, we can then calculate the z-score for all of our mood units. So if you had a mood of 2 that was 2 standard deviations below the mean, or excuse me, 2 mood units below the mean, which leaves us with 1.04 standard deviations below the mean. So if you had a mood of 2, you were negative 1.04 z-scores, or 1.04 standard deviations below the mean. We did that for each of our values. And once we did that, we can then calculate our R coefficient. We take the sum of the z-scores for the x variable times the z-scores for the y variable and divide it by the number of pairs. So I take the z-score for my first x, my y-score, my z-score for my y, my first y-score. Okay, so the first person had a z-score hours slept of negative 1.23 and a z-score for mood of negative 1.4. I multiply those together and I get a z product of 1.28, meaning that the amount of distance that my scores has was 1.28. I add all of my products together, so all of my multiplied x and y z-scores, I add them all together, and I get a total amount of distance from the mean of 5.09. So the total amount of standard deviations from the mean that all of my pairs has was 5.09. If I divide this figure by the number of pairs, I get the mean number of standard deviations away from the mean that each score has, which gives me an R coefficient of 0.85. So the R coefficient is 0.85, meaning that there is a positive correlation, and it appears to be strong, but we'll figure that out in just a moment. So what that looks like is this. The amount of standard deviations, so the amount of total distance that all of these are away from the mean, was equal to about 5 z units. So if I add the distance that 3 is to the mean of 0, so of the z-score of 0, on the x-axis and the y-axis, if I took the distance from 3 to the y-axis and 3 to the x-axis, and I added those all together for each other pair, I would get my value, which was 5.09. And then, if I divide it by the number of pairs, I get the average distance in terms of the R coefficient. So when we're looking at this, we can look for pair 1. So if I see pair number 1, which I've labeled on the scatter plot, it has a z-score on the hours slept axis of negative 1.23. So if I look on my hours slept axis and I have a z-score equal to 0, the first sleep hours is negative 1.23 standard deviations, or has a z-score equal to negative 1.23, or is 1.23 standard deviations below the mean for hours slept. And the mood for that person is negative 1.04, meaning that that person's mood is 1.04 standard deviations below the mean on our y-axis. So so if I look at the mood, it is 1.04 standard deviations below the mean. Each other pair is indicated the same way. The interesting pair is number 2. Number 2 had the mean hours slept and the mean mood for each of those two scales. So that person is at the origin, or has a standard deviation of 0 on hours slept and a standard deviation of 0 on mood. You notice though we still have the same shape. All I've done here was I've centered it so that we have the z-score of 0 for hours slept and the z-score for mood at this origin, this axis here. Now, we're not quite done yet. We've calculated the R coefficient, so we've found the strength and the direction of the relationship. Now we need to know if it is significant. And what we do is we use a T formula to see if that R coefficient is significantly different than 0. Because we know that an R coefficient of 0 is not significant. That's completely uncorrelated. We want to know if it is significantly different than 0. And we can do that using a familiar statistic, the t formula, well, it is a t formula, but it's based on the r values. We're not going to dwell on the formula so much. I want to show it to you, and then we're going to move into what that looks like when we look at our comparison using the normal curve. The strength and the direction of the relationship is indicated by the R coefficient. The sign can be negative or positive, and the coefficient's distance from 0 increases its strength. We need to know if that strength is significant or not when we rely on a t-test to determine it. So the t-value, the number of standard deviations away from the mean our R coefficient is equal to the R coefficient divided by the square root of 1 minus R squared divided by the number minus 2. And in this case, it's the number of pairs. So number of pairs minus 2. And you wonder why 2? Well, it's because each variable has a certain number minus 1. So if you have 2 variables, you need to subtract 2 degrees of freedom, 1 for each variable. So if you have 6 pairs, that comes from 2 different variables. That means you take the 6 pairs minus 2, and that gives you your degrees of freedom. I'm not going to ask you to really memorize or work through this formula by hand, but I'll show you what it looks like when you do it by hand, because it's really not that tough. So if t is equal to r over the radical expression 1 minus r squared divided by the expression n minus 2, you just plug in the numbers that you already have. We know that our r coefficient is 0.85. We found that from earlier, divided by 1 minus 0.85 squared. I recognize there's a little bit of a typo there. Let me fix that real quick. Boop. 0.85, pardon me. 1 minus 0.85 squared divided by 6 minus 2 is equal to the square root of 0.0694. And you divide 0.85 by that radical, which is equal to 0.85 divided by 0.263, which is equal to 3.23. So our t is actually at 2.53. Now I went ahead and took the liberty of developing the comparison distribution at the same time because we can. Our comparison distribution would be a t distribution with degrees of freedom equal to 4. And the cutoff for a t distribution with 4 degrees of freedom to tail at 0.05, which we've done back in chapters, let's see, 8 and 9. We find that our cutoff is in the neighborhood of 2.776. We're going to work through that in the long example. I just wanted to show you what that might look like. So our R coefficient has a t-score, or is 3.23 standard deviations above the mean if we compare that R coefficient to 0. So if we had an R coefficient of 0, it would have a t-score of 0. So we were looking to see if we had a significant R coefficient. We used the t formula to figure that out, and it has a t value of 3.23, which is, by the way, going to be significant. Sorry to spoil it for you. So let's go ahead and move into the hypothesis testing procedure using this example. So again, we can walk through it more linearly. So in step 1, we are going to discuss the research questions, come up with the populations, and we are going to look at the null and research hypothesis. So the research question for this particular example is there a significant correlation between hours of sleep and mood? We are going to be looking at a two-tailed test. You can do a one-tailed correlation, that's fine, but we're looking at a two-tailed test. And the populations are a little bit wonky because we're actually not comparing a sample to a population. We are looking at the correlation between two samples. So we aren't really looking at a population comparison. So really what we're looking at, for the sake of using the usual ways of hypothesis testing, is population 1, which are our samples, are the people in the study. Population 2, which is what we're comparing our results to, is a population whose scores are not correlated. So when we looked at this, we kind of hinted at that this is a distribution of people whose mean correlation is 0, okay, that had an R of 0 or a t-score of 0. We're comparing our sample to a population whose scores are not correlated to see if it is significantly different than that. So that kind of gives a little bit of graphical representation to that statement. So the research hypothesis is that there is a significant correlation between hours slept and mood, or that R is not equal to 0. And we know that what we mean by that is that it is significantly different than 0, or not at all 0. Our null hypothesis is that there is not a significant correlation between hours slept and mood, or that R is equal to 0 or not significantly different than 0. In step 2, we need to talk about the comparison distribution, and we're comparing scores from the same group of people using two different variables. So there's really not a comparison distribution, but we do have characteristics of the sample that we need to discuss. And I'm going to just give you the shorthand version because we did the calculations back in the earlier part of the lecture. So the shorthand calculations are this. We had some X scores for the number of hours slept. We had some Y scores for the mood that the people were in the next day. X minus M, so the deviation scores are listed, and then the Z scores for each of those was listed as well. In step 3, we need to determine the cutoff t-score where we will reject the null hypothesis. So most of the time we're going to use SPSS to tell us if our results are significant, but we can show off by walking through this a little bit. So in the example that we're using, we need to find out if our correlation coefficient is significantly different than 0. And we do that by testing the correlation coefficient against the t-distribution to see if our correlation coefficient is far enough away from a t-score of 0 to be significant. So first thing we do, because in step 4 we'll actually calculate our t-statistic, first thing we do is we find the degrees of freedom. So each variable has 1 degree of freedom, which means that each pair has 2 degrees of freedom. So we take the number of pairs minus 2, which equals to 6 minus 2, which equals 4. We declare that we're using a cutoff of 0.05, and we're using 2 tails. So we look at our t-table, and we find our 2-tailed test at the 0.05 alpha level. 4 degrees of freedom, our cutoff is 2.776, and that's plus or minus. So we are plus or minus 2.776. We will plot our sample's t-score on this to determine if it is significant. So in step 4, we actually calculate our sample's t-score. We do that by finding first the R coefficient and then converting that into a t-score to find out how far away from a t-score of 0 that particular coefficient is. And something that I want to mention now is that you can't just say that a 0.85, which is what we found, by the way, a 0.85 correlation coefficient is always going to be significant, because it really does depend on the number of pairs. If you had only maybe 2 pairs, that might not be significant. 0.85 is a pretty big correlation, so it probably would be significant, but we can't just rely on that. Let's say that we had a correlation coefficient of 0.5. That doesn't mean that it's going to be significant or non-significant, because it really does depend on how many pairs there are. Okay, anyways, we calculated our R coefficient by using the method in the formula by multiplying the pairs Z scores together, adding them all together, and then dividing by the number of pairs, which is indicated in this table here. And our R coefficient is 0.85, meaning that we at least know that we have a positive correlation, but we're not sure how strong it is yet until we look at our t-score. We calculated the distance away from the mean that our R coefficient is in terms of t-scores by taking the R coefficient, dividing it by the radical expression 1 minus R squared divided by n minus 2. When we did all of our calculations, we got a t-score of 3.23. Our sample's R coefficient, so our sample's correlation coefficient, is 3.23 standard deviations away from the mean on our comparison distribution. It looks pretty bad for the null hypothesis, which means that we're probably going to have a significant result. But let's bring it down to the 5th step, where we actually make that decision based on our values using the inequalities. So because it's a 2-tailed test, we need to test the null hypothesis that says that our R coefficient will be somewhere in the fail to reject zone, will be between our 2 cutoff t-scores. We do that by creating the inequality where we put our low critical value, our low t-score for our cutoff, also our high cutoff t-score, and we put our sample's observed t-score in the middle and determine if that statement is true. Because if it is true, then our t-score will fall somewhere in here, and we will consider that to be significant. Or excuse me, to be non-significant. If it's outside of that zone, so if it's either higher than our cutoff on the right side or lower than our cutoff on the left side, then we will consider it to be significant. So if we go through this, we see that negative 0.2776, which is our low cutoff value, is that less than or equal to 3.23? Yes, that's true. So far we know that our observed t-value is greater than our low rejection area. So far it's not significant in the negative. Our next step is to look at the second half of the inequality. Is 3.23 less than or equal to positive 2.776? That is not true. 3.23 is not less than or equal to 2.776, which means that we reject the right side of this null hypothesis equation, which means that we can reject the null hypothesis. And that's indicated visually by where we plotted the observed t-value for the correlation coefficient that we saw. It is in the rejection zone, so we reject the null hypothesis, which means that we have a significant R coefficient. In this case, it's significantly greater than 0. Let's take a look and see what the results section statement would look like if we were doing this for our data analysis. So, a Pearson's R correlation was used to determine the correlation between the number of hours slept, which we called hours, and the mood one is in the next day, which we called mood. There was a significant correlation between the number of hours slept and the mood the next day. The R of 6 pairs equals 0.853, with the p-value equal to 0.031, which I pulled from SPSS. A scatter plot summarizes these results in Figure 4. These results suggest that there is a significant correlation between the number of hours slept and the mood the next day, and we can reject the null hypothesis. I used a scatter plot in SPSS, and I called it Figure 4. It's an arbitrary number. You'll probably call yours Figure 1 because it'll be the only figure in your data analysis. So remember when you include your scatter plot in your data analysis, that it just goes after everything. And you can refer to it as Figure 4 as opposed to plopping in the middle of your output. That's fine. So that is correlation. It's pretty straightforward. It's something that most of us have seen before, even if you haven't gone through the process of hand calculating it. So again, we're looking at the correlation between two scale variables. We're looking for strength, direction, and the statistical significance of the result. If you have any questions, let me know. Otherwise, I look forward to seeing what you can do with your data analyses.